warahmatullahi wabarakatuh. Now today we will discuss about copper-based casting alloys. Now in this copper, if we talk about copper, then copper itself have high electrical conductivity and high thermal conductivity. A variety of electrical thermal conductivity applications are there, and like for example fittings, cable connectors, cable dead ends, spacers, inductor heads, switch parts, different degrees of conductivity. Now the degree of conductivity depends on material and the amount of material in this figure. This figure shows that this silver and all this, they are reducing the percentage of conductivity in the alloy. And the worst is that of phosphorus. A small amount of phosphorus, see the figure shows, as a very significant or very too much deterioration in the conductivity of the material, and that therefore this is to be properly controlled, and therefore less amount of phosphorus should be there in the alloy. Now, copper zinc alloy. If we look into this, this is the phase diagram. Initially, this copper is having a small solubility, and with 32.5% at liquidus and 35% at room temperature. And major phase, this is alpha phase, while having a substantial beta dash phase. See, now alpha phase is relatively soft and ductile, having low strength, while beta phase is hard and brittle. It is hard and brittle, and therefore with the amount of this alpha plus beta phase, the hardness will be given. The hardness strength therefore increases with presence of beta phase, and but at the cost of ductility, of course. Therefore, we have to optimize for a particular application how much hardness we need and how much it will be reduced. Now, similarly, in copper zinc alloy, the color depends upon the zinc contents and changes with characteristic property color to whiter yellow. Now there is flaring. When zinc is there, this vaporization of zinc takes place. Now after vaporization, this zinc gives very blaring white color, which we say flaring. The increase of zinc content at a particular melting temperature, it increases. Now thermal and electrical conductivity decreases with increase in content. Therefore, we have to take in account how much amount of, depending upon the requirement, how much amount of zinc is required. With the zinc content, therefore, we look into phase diagram, then the lowers the liquidus also, and temperature range of the freezing is increasing with increase in zinc content, and therefore this will promote the dendritic formation of the crystals. Now, and moreover, the density of the alloy will decrease with the increase in zinc content. This zinc is that gives dendritic application because the temperature range is wider, and therefore this promotes dendritic segregation. Therefore, non-uniform distribution of constituent is there, and it due to the dendritic freezing mechanism, and also causes less corrosion resistance, and also reduce the property of the copper get reduced with increase in amount of zinc. Another important alloy is tin, copper tin alloy, in which the solidity of tin in copper is in the form of alpha phase. It is up to 13.5 5% during solidification. At lower temperature, it is alpha plus delta eutectoid occurs. Now, long solidification, here also, similar to that zinc, there is a long solidification range, and hence coring, segregation of dendrites take place. Now, this segregation of dendrites causes embrittlement and also restricts the feeding mechanism, and this all due to this delta phase. Now, the percentage was more strengthening than zinc. Now, this gives the phase diagram. You see, and this alpha phase is there, but this delta phase, which are room temperature, this delta phase, this causes embrittlement. Now, therefore, we have to make a compromise with the delta phase. Now, this is an example. You can see the corings have taken place with copper tin alloys, and it is having 26% tin with the silver. You can see the dendrites has been formed in casting products. Now, if we look into the properties, then we can have hardness with the increase of zinc content, and strength as well as bearing quality increases, because the strength get increases, and therefore bearing capacity also increases. Hence, being used for fabrication of gears, worms, bearing plates, turntables, sleeves, liners, etc., etc. Now, because of corrosion, it is used in resistant to corrosion. It is used in marine construction, naval vessels, breezes, dams, hydroelectric plants, chemical processing industries. Alloy of 88% copper, 10% zinc, and 2% 10% tin and 2% zinc, known as G alloy or gunmetal. Now, it possesses a better resistance, all-round resistance, and therefore have an extensive use. Now, bronze is another alloy which is also being used, that is having 20 to 23% tin. Now, it is relatively hard and brittle, but one thing, that when it is being struck, that gives a musical tone, and therefore it is used for casting bells. Now, this gives a figure of phase diagram of copper and lead alloy. Now, you see here it is the percentage of solubility of that lead in copper is very little. It is about 0.002 to 0.005% at room temperature. But very bad thing is that it is present. It doesn't get. It is not very much miscible. Rather, it present as an island distributed throughout the structure. While freezing, they precipitate out as an island, and in the area of those locations where shrinkage process takes place. However, it restricts. But if the amount of lead is more, then this of course enhance meshability, but obstruct the appearance of it. Thus, the alloy is used to fabricate valves and fittings. Now, weak lead island make machining soft, but it produces a discontinuous chip. Now, another is copper aluminium alloy. This is a very important alloy. Now, you can see the phase diagram over here. Now, it is initially with about solubility 7.4% at solidus, while 9.4% at 565 degrees centigrade. But one thing very important, if you look into this phase diagram, then we can see that this is alpha phase, which is soft. But this is eutectoid. 11.8% aluminium gives an electrolyte, and therefore after that, if we cool down, then it gives separate into two different phases, and therefore but this gamma phase, this is hard. Alpha phase is soft, and therefore if we can capture by heat treatment, if we can capture this gamma phase, then of course the hardening can be done, and therefore the quenching for heat treatment. Now if we can control the freezing temperature range, then we can have a sound casting. It is very narrow, and therefore very can be controlled by different mechanisms. And also this thing, the tectoid at 11.8% at 565 degrees centigrade, this gives the heat treatment facility. After therefore, this heat treatment can be done by holding the component at 790 degrees centigrade to 870 degrees centigrade, and then cooling it. Then we again rehard it so that we can optimize strength, hardness, and ductility. Now therefore, among copper-based alloy, the heat treatment aluminum bronze and heat treated copper beryllium has the highest strength, and therefore accordingly it has its own application, lot of application. The narrow freezing temperature range we have seen in the first diagram, it is very narrow, and therefore large solidification shrinkage requires heavy riser and casting of maximum soundness. Less tendency, because that short range gives less tendency to micro shrinkage. Low aluminum content, less 10% aluminium, cannot be heat treated. Now there are different types of copper aluminium alloys. Low aluminium content, that is less than 10%, and if it is less than 10%, it can't be heat treated. However, higher aluminum content, more than 10%, can be heat treated to high strength. Now effect of iron. Iron is also there. It is always being picked up, because sometimes we use steel pots, and while using these steel pots, this copper gets picked up, and therefore necessity to achieve green size. This iron facilitate to control the grain size. But in absence, if it is absence, then coarse grain is obtained. If more than 0.75% iron is there, then freezing begins with delta phase iron. This serves as nucleation throughout the casting, and therefore prevent grain growth, and therefore we can control the grain size. Excess iron content causes to form iron hard spots in casting, and therefore machining becomes difficult. Some other iron-based alloys like aluminium beryllium, which is soluble 2.1% to at 864 degrees centigrade, consists about 1% beryllium. Now can be heat treated, and precipitation hardening can be done. It is the alloy which is having copper alloy, which is having the maximum strengthening and hardening. Nickel-based alloys and bronzes has white color, and also called therefore as nickel silver or German silver. Nickel bronze contains about 10% nickel, and it has got use in hardware and ornamental fittings. Now permanent mold casting and die casting can also be employed while using this copper based alloys, because the freezing range is low, and due to this freezing range, we will have a chilling effect. And grain control can be done. This is all about this copper alloys. Thank you.